141 is another finding from Taylor-Bridge audit of yield protocol, where the concern was about auditing and logging, that delegates could be added or removed repeatedly to bloat logs. For context, when a user added or removed a delegate, a corresponding event was emitted to log this operation. However, there was no check to prevent a user from repeatedly adding or removing a delegation, which could allow redundant events to be emitted repeatedly. The recommendation was to add a require statement to check that the delegate address was not already enabled or disabled for the user, to ensure that log messages are only emitted when a delegate is activated or deactivated to prevent bloated logs. This is generally related to redundant constructs in 157 and broad aspects of auditing and logging in 173 that we discussed in Security Pitfalls and Best Practices 201 module. 142 is a finding from Taylor-Bridge audit of 0x protocol, where the concern was about auditing and logging that there was a lack of events for critical operations. For context, several critical operations did not trigger events, which would make it difficult to review the correct behavior of the contracts once deployed. Users and blockchain monitoring systems would not be able to easily detect suspicious behaviors without events. The recommendation was to add events where appropriate for all critical operations, and in the long term to consider using a blockchain monitoring system to track any suspicious behavior in the contract. This is related to the missing events aspect discussed in 45 of Security Pitfalls and Best Practices 101 module, and broader auditing logging issues of 173, along with principle of compromise recording of 201 we discussed in Security Pitfalls and Best Practices 201 module. 143 is another finding from Taylor-Bridge audit of 0x protocol, where the concern was about error handling, in that the function assert staking pool exists should have returned a boolean to determine if the staking pool existed or not. But it did not use a return statement and therefore would always return false or revert. The recommendation was to add a return statement or remove the return type and change the documentation accordingly. This is related to function return values in 142 and error reporting issues in 175 of Security Pitfalls and Best Practices 201 module. 144 is a finding from Taylor-Bridge audit of DFX Finance, where the concern was about specification, in that the min and max family of functions had unorthodox semantics. Throughout the curve contract, min target amount and max origin amount were used as open ranges, that is, ranges that exclude the value itself. This is unlike the conventional interpretation of the terms minimum and maximum, which are generally used to describe close ranges. So the recommendation was to make the inequalities in the required statements non-strict unless they are intended to be strict, or alternatively document to convey that they are meant to be exclusive bounds, and in the long term ensure that mathematical terms such as minimum, at least and at most are used in the typical way to describe values inclusive of minimums or maximums. This is related to dangerous strict equalities in 28 of Security Pitfalls and Best Practices 101 module, and broad aspects of system specification and documentation in 136 and 137, and numerical issues in 170 that we discussed in Security Pitfalls and Best Practices 201 module. 145 is another finding from Taylor-Bridge audit of DFX Finance, where the concern was about undefined behavior, in that if an operator attempted to create a new curve in the context of the protocol for a base and quote currency pair that already existed, Curve Factory would return the existing curve instance without any indication of that, causing a naive operator to maybe overlook this issue. The recommendation was to consider rewriting that logic such that it reverted if a base and quote currency pair already existed, and provide a view function to check for and retrieve existing curves prior to an attempt at curve creation. This is related to the broad aspect of undefined behavior in 179 and clarity in 188 of security pitfalls and best practices 201 module. 146 is another finding from Taylor-Bitt's audit of DFX Finance, where the concern was about data validation, in that few functions were missing zero address checks. For example, a zero address check should have been added to the router constructor to prevent the deployment of an invalid router which would revert upon a call to the zero address. So the recommendation was to review address type state variables to ensure that the code that sets the state variables performs zero address checks where necessary as a best practice. This is related to missing zero address validation in 49 of Security Pitfalls and Best Practices 101 module, and broader aspects of function parameters in 138, function invocation arguments in 146, two-step change of privilege roles in 162, and data validation issues in 169 of Security Pitfalls and Best Practices 201. 147 is another finding from Taylor-Bitt's audit of DFX Finance, where the concern was about error handling, in that the custom safe approve function did not check return values for approve call. For context, the router contract used OpenZeppelin's safe ERC20 library to perform safe calls to ERC20's approve function, but the orchestrator library defined its own safe approve function. And this function checked that a call to approve was successful, but did not check the return data to verify whether the call indeed returned true. In contrast, OpenZeppelin's safe approve function checks return values appropriately. This issue could have resulted in uncaught approve errors in successful curve deployments, causing undefined behavior. The recommendation was to leverage OpenZeppelin's safe approve function wherever possible, and also ensure that all low-level calls have accompanying contract existence checks and return value checks where appropriate. This is related to function return values in 142, error reporting issues in 175, and cloning issues in 190 of Security Pitfalls and Best Practices 201. 148 is another finding from Taylor-Bitt's audit of DFX Finance, where the concern was about configuration, in that curve, being an ERC20 token, implemented all 6 required ERC20 methods: balance of, total supply, allowance, transfer, approve, and transfer from. But it did not implement the optional but extremely common view methods for symbol, name, and decimals. The recommendation was to implement symbol, name, and decimals on curve contracts to ensure that contracts conform to all required and recommended aspects of the ERC20 specification. This is related to ERC20 name, decimals, and symbol functions in 103 and configuration issues in 169 of Security Pitfalls and Best Practices 201. 149 is another finding from Taylor-Bitt's audit of DFX Finance, where the concern was about data validation, in that although safe math was used throughout the code base to prevent underflows and overflows, it was not used in a few calculations. Although the audit could not prove that the lack of safe math would cause an arithmetic issue in practice, all calculations would benefit from the use of safe math. So the recommendation was to review all critical arithmetic to ensure that it accounted for underflows, overflows, and loss of precision by considering the use of safe math and safe functions of ABDK math where possible to prevent any underflows and overflows. This is related to dangers of integer overflow, underflow we discussed in 19 of Security Pitfalls and Best Practices 101 module, and broader aspects of data validation in 169 and numerical issues in 170 of Security Pitfalls and Best Practices 201 module. 150 is another finding from Taylor-Bitt's audit of DFX Finance, where the concern was about timing and denial of service, in that the function set frozen could be used by the contract owner to front run to deny deposits or swaps. The contract owner could then unfreeze them at a later time. So the recommendation was to consider rewriting the set frozen function such that any contract freeze would not last long enough for a malicious owner to easily execute an attack, or alternatively consider implementing permanent freezes. This is related to the transaction order dependence aspect discussed in 21 of Security Pitfalls and Best Practices 101 module, denial of service in 176, and trust issues in 181 of Security Pitfalls and Best Practices 201. 151 is a finding from TaylorBridge's audit of Hermes network, where the concern was about denial of service by account creation spam. Hermes had no fees on account creation, and so an attacker could spam the network by creating the maximum number of accounts. Recall that Ethereum miners do not have to pay for gas, and so they themselves could spam the network with account creation. The recommendation was to add a fee for account creation and to also monitor account creation and alert users if a malicious coordinator spammed the system. This is related to broad aspects of audit and logging in 173, denial of service in 176, and trust issues in 181 of Security Pitfalls and Best Practices 201. 152 is another finding from TaylorBridge's audit of Hermes network, where the concern was about undefined behavior from using empty functions instead of interfaces, because that leaves contracts error prone. For context, withdrawal delayer interface was a contract meant to be an interface because it contained functions with empty bodies instead of function signatures, which might lead to unexpected behavior. A contract inheriting from withdrawal delayer interface would not require an override of those functions, and so would not benefit from the compiler checks on its correct interface. The recommendation was to use an interface instead of a contract in withdrawal delayer interface, which would make derived contracts follow the interface properly, and to also document the inheritance schema of the contracts. This is related to unused constructs in 156 and the undefined behavior issues in 179 of Security Pitfalls and Best Practices 201. 153 is another finding from TaylorBridge's audit of Hermes network, where the concern was about data validation, in that cancel transaction could be called on a non-queued transaction. Without a transaction existence check in cancel transaction, an attacker could confuse monitoring systems because that emitted an event without checking that the transaction to be cancelled existed. The recommendation was to check that the transaction to be cancelled existed in cancel transaction function to ensure that monitoring tools could rely on emitted events. This is related to data validation in 169 and auditing and logging in 173 that we discussed in Security Pitfalls and Best Practices 201 module. 154 is another finding from TaylorBridge's audit of Hermes network, where the concern was about patching, in that contracts used as dependencies did not track upstream changes. For context, third-party contracts like concat storage were copy-pasted into the Hermes repository, and the code documentation did not specify the exact version used or if it was modified. This would make updates and security fixes on such dependencies unreliable, since they would have to be updated manually. Specifically, concat storage was borrowed from the Solidity Bytes utils library, which provided helper functions for byte-related operations, and a critical vulnerability was discovered in that library's slice function that allowed arbitrary writes for user-supplied inputs. So the recommendation was to review the code base and document each dependency's source and version, and also include the third-party sources as submodules in Git repository so that internal path consistency could be maintained and dependencies could be updated periodically. This is related to the broad aspects of configuration issues in 165, external interaction of 180, dependency of 183, and cloning issues in 190 that we discussed in Security Pitfalls and Best Practices 201 module. 155 is another finding from Taylor-Bit's audit of Hermes network, where the concern was about access control in that the expected behavior regarding authorization for adding new tokens was unclear. For context, add token allowed anyone to list a new token on Hermes, which contradicted the online documentation that implied that only the governance should have had this authorization. It was therefore unclear whether the implementation or the documentation was correct. So the recommendation was to update either the implementation or the documentation to standardize the authorization specification for adding new tokens. This is related to the broad aspects of guarded launch via asset types in 129, system specification in 136, access control in 172, and clarity issues of 180A we discussed in Security Pitfalls and Best Practices 201 module. 156 is another finding from Taylor-Bit's audit of Hermes network, where the concern was about undefined behavior in that contract name duplication left the codebase error prone. The codebase had multiple contracts that shared the same name, which allowed Biddler Waffle to generate incorrect JSON artifacts, preventing third parties from using their tools. Biddler Waffle did not correctly support a codebase with duplicate contract names, and the compilation overrode its artifacts and prevented the use of third-party tools such as Slither. So the recommendation was to avoid duplicate contract names, change the compilation framework, or use Slither, which helps detect duplicate contract names. This is related to broad aspects of programming style, code layout, and naming convention in 97 to 101 of Solidity 101 module, and clarity issues in 188, principle of economy of mechanism in 197, and principle of psychological acceptability in 199 that we discussed in Security Pitfalls and Best Practices 201 module. 157 is a finding from Taylor-Bit's audit of advanced blockchain, where the concern was about patching, in that there was use of hard-coded addresses which may have caused errors. For context, each contract needed contract addresses in order to be integrated into other protocols and systems, and these addresses were hard-coded, which could have caused errors and resulted in the codebase's deployment with an incorrect asset. Using hard-coded values instead of deployer-provided values would have made these contracts difficult to test. The recommendation was to set addresses when contracts were created rather than using hard-coded values, which would also facilitate testing. This is related to tests in 155, configuration and initialization issues in 165 and 166 that we discussed in Security Pitfalls and Best Practices 201 module. 158 is another finding from Taylor-Bit's audit of advanced blockchain, where the concern was about configuration, in that the borrow rate formula used an approximation of the number of blocks mined annually. This number could change across different blockchains and years. The value assumed that a new block was mined every 15 seconds, but on Ethereum mainnet, a new block is mined every 13 seconds approximately. The recommendation was to analyze the effects of a deviation from the actual number of blocks mined annually in borrow rate calculations and document associated risks. This is related to block values as time proxies in 18 of Security Pitfalls and Best Practices 101 module, and configuration and initialization in 165 and 166, and constant issues in 184 that we discussed in Security Pitfalls and Best Practices 201 module. 159 is another finding from Taylor-Pitt's audit of advanced blockchain, where the concern was about data validation, in that there were no lower or upper bounds on the flash loan rate implemented in the contract. This would therefore allow setting it to an arbitrarily high rate to secure higher fees. The recommendation was to introduce lower and upper bound checks for all configurable parameters in the system to limit privileged users' abilities. This is related to function parameter validation in 138, function invocation arguments in 146, and broader aspect of data validation issues in 169 that we discussed in Security Pitfalls and Best Practices 201 module. 160 is another finding from Taylor-Pitt's audit of advanced blockchain, where the concern was about patching, in that the logic in the repositories contained a significant amount of duplicated code, which increased the risk that new bugs would be introduced into the system, as bug fixes must be copied and pasted into files across the system. The recommendation was to use inheritance to allow code to be reused across contracts and to minimize the amount of manual copying and pasting required to apply changes made in one file to other files. This is related to programming style, code layout, and naming convention in 97 to 101 of Solidity 101 module, and broad aspects of configuration in 165, clarity in 188, cloning in 190, principle of economy of mechanism in 197, and principle of psychological acceptability in 199 that we discussed in Security Pitfalls and Best Practices 201 module.